Hey guys, my name is Tomasz Rewak and this is my next project. The name of this project is Rotating Voxels, because this is actually what is taking place in front of us on my screen. We have a voxel space, so maybe let's start with describing what a voxel space is, because it's actually a very fancy word for a very simple thing. It's just a 3D space, so 3D array in this case, that is composed of multiple voxels, and each voxel is a separate cell. The most important feature of one voxel is that it doesn't move, it doesn't change its position, it's stationary. But it might change its properties. And in the case in front of us, each voxel is described with two properties. So one of the properties is its size. So whenever it happens to be within a shape that we want to display in this voxel space, then this cube inside this voxel will be bigger. So this is one of the features. Another feature is the direction in which this box is actually faced. So whenever we display a shape in this voxel space, it will be rotated so that it faces out of this shape. The interior of those voxels, so whichever side is within the object that is displayed, so those faces are blue, so they are darker, and the external faces are white, so they are brighter. And you can see, especially when focusing on those red voxels, I've actually painted them red just because of it, to make this effect more visible. You can see clearly that their position doesn't change. They are rotating, they are changing their size, but they are not moving. The shape within the voxel space is moving, but not the voxels. This is a quite complicated example, because it might not be clear on the first glance what actually is the shape that we are displaying here. So maybe let's jump to a simple example. I will just stop it. And as you can see, I don't use any 3D software to actually generate those animations. I simply wrote all of this in code, and I also didn't have time or will to actually implement a nice interface, user interface. So to load another scene, we will simply uncomment another piece of code. And let's go with this scene. Yeah, this should be actually a good example. So let's load it. And that's it. Wow, yeah, it needed a little time to actually load. Because this is actually running in real time. You can see that we have 60 frames per second in this scenario, though I have to do some pre-processing first, so it might take a little bit longer to actually start up, but yeah, afterwards it should run smoothly. So this is another example. Here we can see clearly what the shape is. So it's a sphere, and we can see that on the boundaries of this sphere, the voxels are bigger than on the outside, and especially here, yeah, the voxels are in such a distance from this sphere that they are not visible at all. And we can also focus on those red red boxes here, and we can see that, yeah, they are not moving, they are rotating, they are changing their positions, but they are stationary. And we can also see a difference between the interior and outerior. So on the outside the ball is white, on the inside it's bluish. So closely to the background here. Another thing is that whenever the ball crosses the boundaries of our voxel space, it appears on the other side. So it's somehow looped. And this actually, it's not actually here but the definition of the voxel space. I simply wanted always something to be actually inside our voxel space, so that there is always something happening here. Yeah, but that's it about this. Maybe I will also I will go to this scene and change one property of our model. And the model, this property actually, the max distance. Now when we load our shape, we will see that it got a little bit thicker. So the wall outside, so the wall, oh yeah, this is especially visible here. So the distance between the interior and outerior is greater now. And you can also see that voxels that are further away from the center, or rather not from the center, but from those edges here. So those voxels further away are smaller, and the voxels that are closer to our sphere are bigger. And this is actually defined by the distance function that I've created. And based on this distance function, the final size of our voxel is determined. So we actually calculate the distance between the shape and the voxel for each voxel in our voxel space. And based on this value, we decide how to actually display it. Yeah, so this is a very simple example. We can clearly say what's going on here, but it's not only about simple shapes. We can also use more complicated shapes here. So maybe let's go back here and load another scene. In this case, it's a bunny scene, even though the model that is actually displayed here is a rabbit. And as you can see, we are actually loading STL files. STL files defines a model in terms of triangles, so it's just a very complex 3D model composed of multiple separate triangles. And I actually take this model, load it into this software, and I voxelize it. So I describe it in terms of this voxel space instead of those triangles. But this gives us an opportunity to actually use a more advanced models, especially that the STL files are mostly commonly used for 3D printing. So there are many models that are actually available. So maybe let's load it and see what's in here. And yeah, this is the same concept. The shape is moving. There are those red voxels that we can visibly see that they are not moving themselves, just the rabbit is moving from one side to another, and we can see that those voxels are rotating so that they always face outside of our shape. Maybe now let's go to a little bit of theory. So I will explain the math behind it, though the math is actually quite simple and straightforward, so it won't take us long, and then I will go back to our first example and explain what is going on there. To do those explanations, let's load a very good tool for 3D prototyping, for prototyping on a canvas, and let's draw something that will reassemble a grid. So I know that those lines are not very straight, but that's okay. Here we have a 2D array. In fact, in our case, those arrays are three-dimensional, but in here it will be much easier to actually show you how this whole thing is processed. And first, as I've mentioned, there is a processing stage and there is a separate stage for drawing. So now first let's talk about the pre-processing stage. Let's imagine that our shape is it's a cloud, so it might be composed of multiple triangles. So each of this line would be a separate line in our case, or in 3D it would be a separate triangle, and then we should rays through it. Each ray actually corresponds to a separate row or a column of our grid. So there is just one ray per column or row, or wherever you would call it in the depth dimension. And we collect all of the intersections that take place here. So we have an intersection here, 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 etc. And as you can see, those intersections of the ray and the shape, not always happen on the intersection with other ray. So we are actually interested in the properties of this shape here and here, but so far we only have an intersection actually calculated here. But one of the important things is that with the intersection we also get the normal vector. So the normal vector is the direction in which this face is actually faced. And this can be also calculated for other things. So as you can see, it always faces out of the shape, and this will actually be used to rotate our cubes located in those coordinates of our voxels. How do we actually translate this point here? It's very simple. So we simply calculate the distance between this intersection point and our voxel cells. So this distance would be probably 1/3, and this distance here would be 2/3. So this is one thing that we do. Another thing is that we simply translate the same normal vector that we've got here on the intersection point. And we do this in all of the directions. So this point would be propagated here and here. This point would be propagated here and here. And thanks to this, in all of those nearest intersection points between separate rays, so I'm not talking about the intersection points between the shape and the ray and those rays, but between rays themselves, we will have the actual values of the distance from the nearest intersection and the normal vector of this intersection. And then we can also propagate those values further, because as you've seen, we not only display the voxels in the cells, those boxes in the voxels that are nearest to the shape, but we can also gradually actually decline their size. And here we would just say, okay, the distance from the nearest intersection in this point is 1 and 1/3, and it also has the same normal vector. And thanks to this, we will be able to actually display a big box here facing this direction and a smaller box right here also facing the same normal vector. And overall, when we do this for all those squares, we get a final product of our voxelization. Of course, we also have to propagate those values further from this shape, and also whenever there are, because this point might be closest to this thing or this thing. So we have to decide which actually of those points is closer to this voxel. And because of this, we cannot do this operation of the voxelization in parallel. Well, probably we could, but it would be quite complicated. That's why this process, this type of a process, is used as a pre-processing in my software. And there is another step that's performed each frame. And this step is actually much simpler. Let's go back here and let's get our grid back. There are two separate things. There is a shape voxel space and there is a global voxel space. Let's imagine that this is our shape voxel space, but our shape is translated and rotated. So the final... Oh, sorry. Let's do it like this. So the final voxel space on which we would like to display this shape looks like this, like those green lines. And our problem is right now this. We want to display a square, so a box in 3D space, in this location, but we only have values calculated for weights and normal vectors in those points. But there is not a, well, it's hard to find a simpler task than this, because we just have to actually interpolate those points, those values from here in here. We do this in a way that, let's say that our weight defined here is equal to half, and then we take a volume of this part and multiply it by this volume. We do this for all of the values on those edges, and finally we get, so each of those values has a weight described as a part of the volume of the whole thing. So all of those volumes actually add up to 1, and they actually act as a very nice weights for weighted average. And finally we get a weight that's here. Maybe it's also maybe it's 1/3, let's say. And we do the same field for the normal vector. And finally we can actually draw our shape based on those values. And of course, when our shape moves, so the relation between our shape and the global voxel shape, voxel space changes, those relations actually change. So the weights of each separate value changes, and also it might be that we will, in the next step, will take weights from other edges, and then the actual size and the direction in which the voxel is faced actually changes. And thanks to this, we can see this nice animation. But also, this step is very simple and fast to calculate, because we don't have to actually use the base shape anymore. All of those operations are actually pretty atomic, because we can calculate this value independently from other values here in the grid, because those are not dependent. We just use the 4 values here, and that's it. So, as I've mentioned, it's quite fast. And this is how I've got this final result that I've shown you. Let's go back here and let's jump into the first example, rotating scene. You can see that I actually load the same bunny instead. Yeah, it's actually a rabbit, but the same model here. The only thing is that I actually rotated in a quite fancy way. I translate it, so it's always moving, it's always in some weird position, so it's hard to spot that it's actually a bunny. But let me close this. No, I don't want to save it. But after I load this, yeah, it's hard to say that it's a rabbit or a bunny. Though it's quite nice to look at. Especially those fragments here when it actually passes through the boundaries of the shape, because we can see the internals, how they pretty quickly rotate and try to actually face the ulterior of our shape. And here we can see the ears, the head and the body, because in this example the distance from the body that we are actually displaying, so those voxels are up to 5 cells away from our shape, and they will still be visible. So yeah. Let's maybe talk a little bit about the code, because this is also an interesting part. Usually when thinking about projects like this, you would think about C++ as the main programming language in which you would like to actually implement it. But in this case, this is actually implemented in C#. I've discovered 2 nice projects. One of them is Alea GPU. I don't know if I pronounced it correctly. It's ALEA. And this is a software that enables you, well, this is a library that enables you to use C# for creating CUDA kernels. And this actually translates your C# code into this CUDA kernel, so you don't have to use any other translators, converters, or anything like this. And you can actually pretty straightforwardly call it from your code. So let's take a look at the very simple kernel. In this case, this is a clear kernel, which we call before we draw anything on the canvas. So before we actually populate a global voxel space with a shape voxels values. And this, so it calculates the start and end index of cells that you would like to clear based on the block index and thread index. And then it simply assigns a new voxel face to it. It's pretty straightforward. And if you look at the clear method that simply calls this clear kernel, it's also very simple. We specify which kernel we want to call. Internally, it will translate this code into the CUDA code, but it happens on the runtime, I think. It's like with the link statement used in the entity framework. And you also have to specify the params of the call, which is the number of parallel operations that we want to actually perform. And we can also pass some parameters. In this case, we pass the pointer to the array that we want to clear, and this array is actually located on the GPU. So this is the thing that we'll be filling, but also if we have something that's defined on the CPU, the Alea GPU will actually take place of moving this to the GPU when we call it. In this case, I didn't want to do it because whenever I do this preprocessing stage, I have actually the voxel space of the shape ready, so I load it just once. I don't do it multiple times each call, and thanks to this, when I actually want to display something, I want to add a shape to a global voxel space, I simply have to send those two pointers, so the pointer to the shape and the space, which are already located on the GPU, and the transformation matrix. The transformation matrix by which I want to actually transform my shape. And also some few less relevant parameters. So this max distance parameter and the revert parameter, because some of the shapes in the STL files are oriented differently than others. So the faces might face inside or outside of the shape. And if you look at the kernel, it's just a C# code. Of course, there are some limitations, so you won't be able to use classes. You have to define all instructs, but this is expected because structs are much faster because you don't have to actually allocate them. Another thing is that you cannot use constructors for those structs, which is a little bit strange limitation. But it's very easy to overcome simply by using static functions which actually create those structs and initialize them. So it's not that big of a deal. And apart from that, it's quite straightforward to actually write those kernels. Another project that I've used is the OpenGL.net. Unfortunately, you cannot create shaders in C# because it's quite a different language, so it would be pretty hard to actually translate. So all of my shaders are handwritten. So this is a face shader, very simple. I just have some logic here so that on edges I can display those little bit darker parts so that you can see where the shape ends, especially if there are multiple nodes, multiple voxels on this with this biggest size next to each other. It would be hard to spot any difference, and it would be just flat surface because I'm not using any shading there. And this is the Vertex shader. This is where all of the magic happens. So I load a texture, and the texture is where I defined weights and normal vectors of each voxel, and based on the index of the instance that I'm actually currently drawing, I get this value from the texture, and I display a box in this location. So the texture is generated in CUDA, and after it's generated, I pass it into the OpenGL, and using its instantiating mechanisms, I display those boxes in this grid. The nice thing about this instantiating mechanism of OpenGL is that you don't have to actually do multiple calls to the GPU. You just call it once, you say that you want to display, let's say, 4,000 cubes, and simply pass some differentiating parameters so that all of those cubes might be displayed differently, but the OpenGL takes care of actually calling your Vertex Shader multiple times for those instances and draws them accordingly. It's very simple as compared to actually calling a draw method separately for all of our cubes. And when it comes to OpenGL.NET, you can see that it provides very simple interface, so it's very similar to what we get in the C++. If you know OpenGL from C++ or maybe from Python, then it's very simple to actually write some code in C# as well. And I think that's it when it comes to this program. So you can see that, yeah, it's a C# code, which is pretty nice. So probably all of my next projects concerning, well, about using the CUDA will be probably written also in C#, because it's much easier to actually set everything up here for this project, because I just had to actually install one NuGet package for CUDA support. I don't have to actually install any external components, and I also don't have to worry about the compiling with multiple compilers. I simply install a NuGet package and run my software, and that's it. So it's just working out of the box. Of course, we are not only limited to displaying one shape, we can also display multiple shapes. In this case, it will be two spheres. And you can see that, yeah, on the intersections, they are merging together, they are using the same voxel space. But the thing is that they have to be actually loaded one by one. So we cannot calculate this in parallel for multiple shapes. We have to first, actually let's take a look at this multi-shape scene. We first clear the whole voxel space, then we add one shape in one location based on the transformation that we define here, and then we load another shape. And when we look at this method, we can see that it actually synchronizes the GPU thread after launching the kernel. So so it's drawing it shape by shape. So it's not a very good method if you want to draw multiple shapes in our voxel space, but it's quite nice when you want to display just one of them, just one shape. At the end, let's load the same thing that we were looking at the beginning, because it looks quite nice in my opinion. And with this accent, let's end this video. Thank you for watching and hope to see you in the next episode.